this is Math466, Advanced Applied Analysis. This is Lecture 8. So we're going to continue our evaluation of series and sums. And we're going to try to use complex analysis. We're going to try to use Fourier series, which is related to complex analysis, to understand these. And it's very similar to what happens in combinatorics. You want to understand something that's hard, and you show it's equivalent to something else, and you have a formula that allows you to deal with one, and you use that to pass to another. Where you recognize that what you're studying is really the same as another problem. And so we saw that we could find the sum of 1 over n to the 4th by seeing that it's the sum of the squares of the Fourier coefficients of something. And we had Bessel's equality, which is also called Parseval's equation, that related to the sum of the squares of the Fourier coefficients to the L2 normal of the function. What if we wanted to evaluate not the sum of 1 over n to the 4th, but the sum of 1 over n squared? So we did 1 over n to the 4th, and we got that because the Fourier coefficients looked like 1 over n squared, and so when we squared them, we got 1 over n to the 4th. And this only held at the odd values, but that's not a big deal. If we can do it for the odds, we can do it for the whole thing, because the whole thing is the evens plus the odds. The evens is just, since we're doing it to the 4th power, 1 over 2 to the 4th times the original thing. So you get 15/16. How could we get just the 1 over n squared? So we studied, I think it was f of x equals 1/2 minus absolute value of x on minus a half. We had the 0th coefficient was 1/4. The easy way to see this is to just find the area of the triangle. The 0th coefficient is always just the area under the curve, or the sine area under the curve. And then we got f hat of n equaled, I think, 0 if n was even. And then if it was odd, does anybody have the value as like a -1 over 2k plus 1 squared? N equals 2k plus 1. Was it -1, or was there an I? Does somebody have the value from last time? Okay, so it is
pi squared.
Okay, -1 pi squared?
Pi squared is
in the denominator, right. That's right. We needed the pi squared. Good. So we have the Fourier coefficients. Unfortunately, if we look at the sum of the squares, we're going to get something to the 4th power. So we would have to try to find a function whose Fourier coefficients were like 1 over n. Right? Because then if we squared, we'll get 1 over n squared. So the goal is to find out what is the sum of 1 over n squared. And so one approach is to find a function whose Fourier coefficients are 1 over n. The problem with that is convergence properties. So let's say we were lucky enough to find a function whose Fourier coefficients, say g hat of n, is like some constant over n. Then we could apply our formula, and as long as we could integrate g, we'd be okay. The problem is SNG of x would be a sum and goes from -n to n of constant over n e and x. What might make you worried about studying this? So why might you be a little bit worried about studying this? It might not converge. Why might this not converge?
Sum of 1 over n for large n does not converge.
Yes, so can you give me a value of x where this could be bad? 0. So if you take x equals 0, you're going to get the harmonic series which diverges. So this function will blow up at x equals 0. And in fact, if x is a certain rational multiple, if x is a rational number, you'll have problems at those points as well. So this series would have terrible convergence properties. We need to have the Fourier coefficients decaying faster than n if we want, faster than 1 over n if we want to have convergence. So unfortunately, trying to find a Fourier series like this and using Parseval, using the Bessel equality, is not going to be useful for us. Any other thoughts as to how we might get something for the sum of 1 over n squared? So looking at a different function is going to be very problematic. We're not going to find a nice function whose Fourier coefficients are like constant over n. The answer is on the board. So it's not going to be using Bessel's equality, because that's going to square things. But what could we do instead? What could we do with our function? What could we do with its Fourier series? So let's go back to our function f. We have its Fourier coefficients. What's the Dirichlet series attached to this? No. Sn f of x is going to be the sum. It goes from. Let me figure out how we're going to do this. Essentially, my minus n halves of -1 over 2k plus 1 squared pi squared e to the 2k plus 1 of x. Or maybe a better way of writing it is negative n less than equal to 2k plus 1 less than equal to n. Choose all the frequencies between minus n and n. I want to try to understand the sum of 1 over n squared. How can I get that from this function? So we've got a function here. Where would you like to evaluate this function? Sorry? We want to evaluate between -1/2 and 1/2. Any particular point between -1/2 and 1/2? Probably 0. What would we get if we plug in 0? What is e to the 2k plus 1 of 0 equal? 1. What are we left with? The sum of 1 over r squareds. Right? So if this function is converging to our original function, then here's a way to evaluate. So another way to calculate sums like this is to evaluate its special points. So let's just assume for now that it converges. Assume converges. Assume the limit as n goes to infinity of Sn f of x equals f of x. Let's see what that gives us. Then, if we look at x equals 0, we would get twice, or maybe -2, the sum k goes from 0 to infinity of 1 over 2k plus 1 squared pi squared equals what? It was a half. So
I keep it negative.
yeah, that's what I'm. Are we sure that the four coefficients was -1? Integrate. So the function we're looking at was 1/2 minus absolute value of x. And then this function is even. So the cosine term is the one that matters, the sine term doesn't. So we just want to integrate this against cosine of 2 pi I x. X goes from -1/2 to 1/2. Once again. Mathematica is not simplifying it as nicely as before. So let me just do the integral again right now. Alright, so at x equals 0, the function is definitely 1/2. Alright, so let's calculate things again. So we want to integrate minus 1/2 to 1/2 of f of x e to the negative I to the I, and this is supposed to be a negative sign for that. Oh, that's something like that. Okay. So this is going to just be integral minus 1/2 to 1/2 of f of x cosine 2 pi nx plus I sine 2 pi nx dx. Because this is even and sine is odd, the integral against sine is 0. So we're left with just this against the cosine. So it's twice the integral from 0 to 1/2 of now it's going to be 1/2 minus x cosine 2 pi nx dx. Okay. So now, when we integrate 1/2 cosine, what's the antiderivative of cosine? Negative sign. So the negative means we switch the orders of integration. So we'll have the sine of 2 pi nx, and we divide by 2 pi n at 0 and 1/2. Let's watch the order and make sure we don't make a mistake. And then we would have minus 2 integral from 0 to 1/2 of x cosine 2 pi nx dx. When we look at the sine term, the sine of 0 is 0. The sine of 1/2, look at the sine of pi nx. And the sine of pi nx is negative 1 to the n. I'm sorry, no, the sine of pi n. And so if n is even, it's going to be, it's still 0. So these all, I think this is always 0. Yeah, it's always 0. Okay. So at 0, sine is 0, and sine of, pi n, 2 pi n, 3 pi n, 4 pi n, they're all 0.
Yeah.
Okay, so this piece vanishes. So we're left with minus twice the integral from 0 to 1/2 of x cosine 2 pi nx dx. Okay. So now, let's check the rest of the algebra. So now we'll just integrate by parts. Yeah. It's not bad to do one of these calculations really carefully. So we have negative 2 integral from 0 to 1/2 of x cosine 2 pi nx dx. So u equals x, du equals dx, dv is cosine 2 pi n x dx. V is going to be negative sine 2 pi n x over 2 pi n. So then we'll have the uv term. And so the uv term, when x equals 0, the lower boundary term vanishes. When x equals 1/2, we will have negative sine. Oh, but what's the sign when x equals 1/2? We'll have the sine of pi n. 0. So the boundary term vanishes.
Yeah.
So the boundary term vanishes. Now we have the v du, the minus sign reinforces with that, and we'll get twice the integral from 0 to 1/2 of v du.
Yeah.
So that'll be sine of 2 pi nx over 2 pi pi n dx. Okay. So now, when we integrate sine, we get minus cosine. No, we get cosine.
Yeah.
So this will be 2 over 2 pi n means 1 over pi n, integral from 0 to, right, so it's going to be cosine of 2 pi nx at 0 and 1/2, and then we have to divide by 2 pi n again. Right? And so now, we're going to get pi squared n squared over 1, and then we'll have cosine, when n equals 1/2 of cosine pi n minus cosine of 0 over 2.
So you can see the minus sign now. Like integration of sine is negative cosine, right?
Oh, okay, okay. So the derivative of cosine is minus sine. Okay, good. So there's a minus sign over here. So we have to switch the order of integration.
Yes.
Good. Thank you. There's the missing minus sign. Thank you. And so now, if n is odd, cosine of pi n is -1. These reinforce and we get 1. If n is even, then cosine of pi n is 1 and it cancels. So we get that it's just equal to 0 if n is even, and 1 over 2k plus 1 squared pi squared if n is odd. Okay, good. So somehow we had an, yes?
Yeah.
So somehow we had an extra minus sign. Okay, so fortunately everything we did last time, we just squared things, so in minus sign, squared is 1, so we're fine. So we drop the minus sign here, and now we don't have the minus sign here, and now things make a lot more sense. Okay. We now have a sum of non-negative items as non-negative, as opposed to being negative. Always do sanity checks like this. One of my students from Brown years ago did a sanity check like this in finance because the result didn't look right and found that a minus sign had been dropped in some of the calculations. All right, so we now know that this sum is 1/2. So equivalently, we can now deduce that the sum goes from 0 to infinity of 1 over 2k plus 1 squared is pi squared over 4. Right. Now we can use that to actually get a good sum. So what do we get? So we have the sum n goes from 1 to infinity of 1 over n squared is the sum n even 1 over n squared plus the sum of 1 over n squared n is odd. We know what the odd sum is. That's just pi squared over 4. The sum over just the evens. So I have n equals 2, 4, 6, 8. I just pull out a 2 from each one of them. And because I square, that's 1/4. So this is just 1/4 the sum over all n of 1 over n squared. To see that, just write n equals 2m. And so if we write n equals 2m, then 2m squared is 4m squared. And now here n ranged over the even numbers, n ranges over all the non-negatives. Well, actually all the positives. So now the sum that we want is 1/4 of the sum we want plus pi squared over 4. So this is the bring it over method. The quantity we want is on both sides, and it doesn't have a constant of 1/4. So if we subtract, we get 3/4, or equivalently, the sum n goes from 1 to infinity of 1 over n squared is 3/4, so this becomes 4/3 pi squared over 4. Alright, so
Sorry, could you score that step one more time?
You have
Sure.
the 2.
And we dropped to 2 somewhere. So.
Yeah.
Okay, where did we drop to 2?
At x equals 0 2 times, you derive the 2 times.
Yeah, just go to the second line again.
Oh, okay, well, I thought I put that
Yeah.
over there with the 4.
Yeah.
Okay, so going from here to here?
Yeah, no, go from the first line, second line.
Okay.
Yeah, just that middle term.
So if I take n as even, I can write n as 2 times m.
Yep.
So n squared is 4m squared.
Yeah.
If you want, I can write this as m
Oh,
goes
yeah.
1 to infinity,
Yeah.
and then just replacing m with n.
Oh, you dropped it back.
Okay, where did I drop it?
Cosine 0 minus cosine pi n over 2, you derive the 2.
No, because when n is odd, we get 1 plus
2.
1 over 2.
Yeah.
So it's 1 over 2k plus 1 squared pi squared.
Right.
And so this is going to be twice of our sum, and when x equals 0, we get 1/2, so it becomes 1/4. This becomes 3/4. Becomes 4/3. So we're getting pi squared over 3, but the answer is pi squared over 6. This is the second time in a row there is a painful algebra mistake. So when x equals 0, oh, that's what I'm thinking. That's why mathematics was giving me the answers. I put an I over there. Okay. So when n is odd, it should be n squared pi squared. Okay, so that should be correct. And so now, only the odd terms are surviving. So this is the same as twice, just doubling all of those. And it is equal to 1/2. It should be 4. Somehow I don't think all of math has changed over the weekend. It's supposed to be pi squared over 6, not pi squared over 3.
Yeah.
And it's f of 0. Okay, now I see the mistake. F of 0 is not 0.
So
F of 0 is a 4th. Right? This is the sum. We're supposed to do the sum of all the Fourier coefficients. It's not just the odd ones. There's also f of 0. Right?
Okay.
And so we said, look, all the even ones vanished. It's not the case that all the evens vanished. All the evens vanished except n equals 0. N equals 0 is 1/4. Forgot f hat of 0 equals 1/4. So this is really 1/2 minus a 4th. And 1/2 minus a 4th is 1/4, which is half of what we had a moment ago. So that gives us a pi squared over 8. All right, mathematics is consistent, thank God. All right, so then this becomes an 8 over here, this becomes an 8 over here, and this gives us now pi squared over 6. And we've now just found how to evaluate the sum of 1 over n squared. This is one of the most important sums in mathematics. I will prove in a few minutes how this implies infinitely many primes. All right, I'll prove it implies infinitely many primes first, and then we'll talk about whether or not what we've done is legitimate. So is everybody comfortable with this algebra? This is all relying on one assumption. What is it that we've assumed?
That converges.
That it converges. Do we know that it
Yeah.
converges?
No.
No. We do know the phase series converges, and the phase series is a weighted version of this that will converge to this in the limit.
Yeah.
So we could argue that this is still legitimate because the phase series is fine, and in the limit will converge to this. So as long as both series converge, as a nice exercise, you can show that this would be legitimate. Did we prove that the Dirichlet series converges? What do we need for the Dirichlet series to converge? Differentiability. Do we have differentiability? Not as, so we're only missing differentiability at one point. That's not that bad. Oh, by the way, what point are we looking at? The one point where we don't have differentiability, right? So everything is fine everywhere except at the point x equals 0, which is the one point we want to use it right now. All right. So if everybody's comfortable with this, I'm going to erase this, prove that there are infinitely many primes, and then we'll go back and we'll figure out, is this valid? So has everybody here seen the Riemann zeta function? Zeta of S is the sum, n goes from 1 to infinity of 1 over n to the s. At least if the real part of s is greater than 1. Has everyone seen this function? Okay. It turns out by the fundamental theorem of arithmetic, this is the same as the product p is prime of 1 minus 1 over p to the s inverse. What is the next prime after 2017? Okay, too long of a wait. What is the next integer after 2017? Much better, right? There is really no mystery in the distribution of integers, right? We know a lot about the distribution of integers, the wait time to the next integer. We actually have an explicit formula for the nth integer. F of n equals, and yeah, it's really not that hard, okay? The idea is to take the integers, which we understand, and pass from knowledge there to knowledge about the primes. So the way you prove this is the geometric series, and you just expand things out. Okay, it's not too bad. Okay, if you take s equals 1, and take the limit as s goes to 1 from above through real values, this is the harmonic series. The harmonic series diverges. If there were only finitely many primes, this would converge. Therefore, limit as s goes to 1 from above implies infinitely many primes. If we take s equals 2, what's the sum of 1 over n squared? Pi squared over 6. So when we take s equals 2, this is called a special value proof. We get pi squared over 6 is the product, it's annoying that the pi's and the products are very similar, over p prime 1 minus 1 over p squared inverse. What kind of number is pi squared? Irrational transcendental. So all we need is this is irrational. There is a straightforward proof that this is irrational by doing a bunch of integrals and seeing that if it was rational, you would end up having an integer strictly between 0 and 1.
So the fact that it's irrational tells us that there's
infinitely many primes.
Infinitely primes, yeah.
So if there were only finitely many primes, what would be true about a finite product of rationals? Rational. So because this is irrational, there must be infinitely many primes. So contradiction unless infinitely many primes.
So we have the product of infinite rational numbers is irrational?
No. We have an infinite product of rationals can be irrational.
Can be irrational.
An infinite product of irrationals could be, an infinite product of rationals could be rational or irrational.
Right. But the finite product of rationals is rational.
Finite product of rationals is rational. So as a nice exercise, come up with an infinite product. If there was homework this week, that would be a great problem. Come up with an infinite product of rationals that converges to a rational. You can do that. But we know that if there were only finitely many, it would have to be rational. And since pi squared is irrational. So back when I was a postdoc at Brown, there are ways to talk about how irrational a number is. And I was able to use that to get some proofs about how many primes there are less than equal to x. And so the prime number theorem says the number of primes at most x is about x over log x. I was able to prove that there's at least log x primes up to x initially. Even Euclid's argument gives you log x. And so it's not a great result. And the result turns, that I'm getting log x primes. My count is much worse than the truth, and it's much worse than what Euclid got. And also it turns out that I was assuming the prime number theorem, because I needed a result about how irrational pi squared was, and the paper I was using used the prime number theorem to get a statement about how irrational. So by assuming that there are x over log x primes at most x, I was able to prove that there are at least log x primes at most x, which is not as good of a result, and it's a lot more work. So with some students, including some recent Williams alums, we were able to actually push this a little bit forward and almost get the prime number theorem holds infinitely often by just knowing things about how irrational this is. And I'll include a link to that. So we have these special value proofs, we have these functions, and these sums appear in trying to understand these functions. And the whole idea is we want to relate something we care about to something we can study. All of the stuff we're doing in Fourier series, it occurs in a variety of places in mathematics. But we want to be able to understand these sums. So the problem is this pointwise convergence. We do not know that the function Sn of f is converging to our function. We would love to have pointwise convergence. Now, as I said, you could go through and say, well, if we know the Fourier series converges, and so we could do Fourier, we would have now a sum, maybe negative n less than equal to 2k plus 1 less than equal to n. We would have n minus the absolute value of 2k plus 1 over n, 1 over 2k plus 1 squared pi squared would equal f of 0 minus f hat of 0. Okay? This is a theorem. And then we would show that as n goes to infinity, this is going to converge to the sum that we want. And then we would be okay. So that's one way to make the proof rigorous, is to work through the Fourier series. So I actually went up and met with my brother this weekend to talk about Fourier series versus Fourier series, because he works at MathWorks. And I asked him, do you ever really use Fourier series? No. So a lot of times these are theoretical tools to allow us to get to certain calculations. One of the homework problems this week is to actually see which does a better job approximating Fourier series or Fourier series. If the Fourier series does a pretty good job, it's a little bit easier to use because you don't have to include the weights. And you are sometimes worried about how many computations you need to do. So the question is there a way to somehow save the Dirichlet series theorem, to save the Fourier series argument? We would love, we want Sn f of 0 converges to f of 0. The problem is f is not differentiable. Okay? How many of you have read Asimov's article, The Relativity of Wrong? I know I sometimes send this to my students. I'll try to remember to send this to you. Not all failures are equally bad. So he talks about people used to think the Earth was flat, and then after that people realized the Earth isn't flat. It's what is it, a spheroid. Then they realize it's not a spheroid, it's a oblate spheroid. And then there are some people who go, well, we can never understand the truth of anything, and everything is wrong. And Asimov goes, if you think the difference between being an oblate spheroid and a spheroid is as wrong as sphere to flat, you're even wronger than all these other people combined. There's relativities of wrong, and you're at the top of the list. Okay? Our function f is not differentiable. But how bad is our function f? And this is where new concepts in math come from. And then the difficulty is, plus we have to add plus 1/4. Negative n value of x, -1/2, less than equal to x, less than equal to 1/2. It's differentiable everywhere but the origin. How badly is it not differentiable with the origin? We know the plot. This is almost the limit of my artistic ability. So our function is not differentiable at the origin. How close is it to being differentiable? So we're going to introduce a new mathematical concept today. It's exciting. If I define my function on the interval 0 to 1/2, is the function differentiable? Yeah. F is differentiable on the interval 0 1/2. What about on the interval -1/2, 0? Yes. So f is differentiable on both of these sets, but it's not differentiable on the greater region. Why is it not differentiable?
Slope goes from -1 to 1.
Yeah, the left limit and the right limit don't agree, but they both exist. So the left and the right derivatives exist but are unequal. So left, right derivatives exist but unequal. So even though it feels to be differentiable, it feels to be differentiable in essentially the nicest way possible. Right? The best thing you could have to be differentiable means left and right derivatives exist and they're equal. It's just ignoring the little part at the end and are equal. So then the question becomes, how bad is it in all the things we're doing to have the limits exist but not be equal? So now we have to go back in time and remember what we were doing when we were doing Dirichlet's theorem. So, proof of Dirichlet. So we had basically Snf of x minus f of x, something like this. And we had an integral -1/2 to 1/2 of f, I think it was like x minus y minus f of x. And then we had the Dirichlet kernel. And the Dirichlet kernel was, I think, the sine of 2n plus 1 pi of x over, was it like n sine pi of x, I think? I think that's what the Dirichlet kernel was. And I think here, these were y's, not x's. Right?
You don't have the n. And the denominator.
Oh, there's no n in the denominator? Okay, it's just sine of 2n plus 1 pi y over sine pi y? Okay, great, yes, thank you. And then what we said is, let's write this as a y over here and a y over here. And then we could actually move the sine of pi y over here, put a pi there, put a pi there. Or actually, I guess maybe we want to put a pi here. And what we said is, because f is differentiable, this limit exists. This was f prime. This limit exists. And we use the Riemann-Lebesgue lemma. And so when we use the Riemann-Lebesgue lemma, we were getting the Fourier coefficient. And we know the Fourier coefficients go to 0, so this is going to 0. But when we proved the Riemann-Lebesgue lemma, we didn't need this function to be continuous. We just needed this to be like a nice L2 function. So all we need is that this limit exists. Well, for the limit to exist, that's differentiable. Okay, do we really need that, or do we just need that this is integrable? if we're just missing it at one point, if we change our function at one point, how much are we changing the value of the integrand? We can break this up. Y less than equal to epsilon plus y greater than equal to epsilon. We can choose epsilon as small as we want. This quotient is bounded. So the contribution from this we can make as small as we want because it's bounded. We don't need differentiability. We just need that this ratio is bounded. So this is the new concept. So we need the limit as h goes to 0 of f of x plus h minus f of x over h to be bounded. So another way of saying this is maybe maximum, 0 strictly less than h less than equal to delta is less than equal to some b. That in some small neighborhood, no matter how small we make h, this quotient doesn't grow too much in absolute value. That's all we really needed. We don't need the notion of differentiability. So this will lead to things that are called like Holder conditions or Lipschitz conditions, where you are just assuming certain things about these difference quotients. And it's a slightly weaker assumption. And you can ask, who cares? Why do we need these weaker assumptions? Well, when we're looking at the Fourier series, our function, 1/2 minus x, this is the triangle function. The triangle function is a very natural one to look at. Another natural one to look at is a square pulse, on, off, where it just flips the switch and goes from being on to being off. And you have discontinuities. You need to have a theory that's rich enough to allow you discontinuities, to allow yourself points of non-differentiability. And the whole notion about all of this is that there is a way to extend what we're doing. So there are two paths to this. And again, a huge part of this course is to try to help you think about how should you attack things like this. One way in mathematics is always go to a theorem that you have and see, can I modify it to apply to this situation? So one way was to run back to Fayet's theorem. We know we have convergence with Fayet's theorem. Fayet differs from the Dirichlet theorem for these small weights, and these weights converge to 1, and they converge to 1 from below. So you can look at the difference between the two series, and you can show that as n goes to infinity, the difference goes to 0, therefore you're fine. So one way to prove all of this is to just use Fayet's theorem. The other way is to go back and open up Dirichlet's theorem. And what I love about this is this illustrates a great warning. Just because we prove something in one way does not mean that that is the only way to prove it, and it does not mean that these are the conditions that you must use. We're putting on conditions that are natural for us. We've talked about what it means for a function to be differentiable, so when we see a quotient like this, in our mind, when we see this, we think we want our function to be differentiable. But it's worth stepping back and saying, what's the minimal condition, what's the minimal fact I need about this quotient in order for the rest of my proof to work? I need this to basically be bounded. And as long as this is bounded, everything is fine. I need this function to be in L2. Everything is fine except at that one point. And now we have pointwise convergence. And what's really nice is, if you just evaluate your function at 0, well, all the en x's of 0 is just 1. And so now these Fourier series sums, you can actually evaluate them if you can just evaluate your function. Which would you rather do, evaluate a function or evaluate an integral? Typically, I would much rather evaluate the function. Especially if it's a function like 1/2 minus absolute value. I can evaluate that. Now, if you're trying to evaluate a function at a place where it's discontinuous, I would be very worried as to what's going on with the Fourier series. It might not be unnatural to suppose that it's converging to maybe the point between the two values. But things will be a little bit subtler there. It's nice to have at least continuity in your function. Physically, do you think you can have something that's discontinuous? Where the pulse immediately starts and goes to full force? Or is there some small ramp-up time which might be really small? So for a lot of things, it's nice mathematically to model them with a discontinuity, but in actuality, there is a very rapid crank-up happening. Okay, so this is basically all I wanted you about, summing series, your best possible stuff like that, pointwise convergence. The point is to show you the power of these techniques, that there are certain sums that we can now get. If we want to get the sum of 1 over n to the 6th, can we find a function whose Fourier coefficients are like 1 over n cubed? Or can we find a function whose Fourier coefficients are 1 over n to the 6th and use like Dirichlet theorem for pointwise convergence? This gives you a new technique to evaluate these things. What we'll do now on Wednesday's class is you should make sure that you're comfortable with the definition of the Fourier transform and Poisson summation. Poisson summation is the last of the really powerful Fourier techniques we're going to need, and then after that we will then move into, I think it's chapter 9, which is benefits law. So you should have already started reading chapter 9. Alright, so this is a good place to stop.